All right, hello everyone. So now we're going to go ahead and jump into our Chapter 8 slides. These are pretty short, so this video shouldn't be too long. I'm going to include practice problems within this video too, so that we don't have a lot of videos hanging out in Moodle. But it is important though that you watch the video that I have linked to this video on YouTube, because it does a really good job of explaining sampling distribution. So I'll talk more about that when we get to that slide here in a minute. So let me share my screen. Okay, so here's our Chapter 8 slides. We're going to be talking about sampling distribution and different types of samples. The chapter does talk about confidence intervals, but we pick that up in Chapter 9, so I have excluded the confidence intervals part from this chapter, so you don't have to worry about that for the test. Okay, so now I want you to pause my video and go to the video that I have included in the description of this YouTube video. It's a Khan Academy video that talks about sampling distributions, what it is, and it gives an example of it. It's a really good, really descriptive way to describe, I guess, sampling distribution. So now I want you to watch that. Pause me and watch that. And when you come back, then we're gonna continue our lecture. So here we have our definition of sampling distribution. So it's a theoretical distribution of a statistic based on all possible random samples drawn from the same population. So here we've got a theoretical distribution like we learned in Chapter 7. A theoretical distribution is one that is based on math and logic rather than actual data being drawn. So it includes all possible random samples drawn from the same population. So another key word here is random samples. And we talked a little bit about sampling earlier in the quarter. So when we are gathering data, because it's difficult to gather data on this whole population here, we gather samples. And there's a lot of different ways to do sampling. And the best way, the way that we want to try to do sampling, is random sampling because it is unbiased. And what random sampling is let me go ahead and write this out on here. So, random, all people in population have an equal chance of being sampled. So a random sample is one in which every person in the population has an equal chance of being sampled for the study. So random sampling is really hard to do. It's difficult to randomize our sampling conditions, so it's not always done. However, this is kind of the holy grail. This is what we strive for. So a random sample is one in which everybody in the population has an equal chance of being sampled for the study. So sampling distributions involve random samples being drawn from the population. If our scores are distributed normally, so this kind of gets back to what I was talking about in Chapter 7, we can use z-scores to determine the probability of a particular occurrence. So if our theoretical normal distribution and empirical normal distribution overlap, we can then convert our raw scores to z-scores and find out the probabilities of those z-scores occurring. So be attentive to sampling distributions because they are at the heart of inferential statistics. And if we remember, inferential statistics are the ones where we can infer something about the population given our sample data. So that is that. Okay. So here is basically what I was saying earlier. So a random sample is a subset of all the population chosen so that all samples of a specified size have an equal probability of being selected. This is a good thing and we need it when conducting research. So random sampling, like I said earlier, is the holy grail of sampling. It's where everybody who is in the population has an equal chance of being selected to be in the study. However, this is really difficult to do in the real world. We try to do it, but it's not always possible. To use a sample, this is another important point about samples. To use a sample is to agree to accept some amount of uncertainty about the results. And we've talked about this before in previous classes, that anytime that we're using sample data and we're not gathering everybody in the whole population, there comes some uncertainty with that because we're not gathering all pieces of information, only some pieces of information. So that comes with some error and some uncertainty, so we have to keep that in mind. And here we have an example of a population and people being sampled from that population here. So like I was saying earlier, sampling distributions allow you, so we can have uncertainty with our sampling distributions. And a good thing about our sampling distributions is that we can measure that level of uncertainty given the amount of people that we have in the sample and that sort of thing. So this is a really good thing about sampling distributions. If there's a lot of uncertainty in our sample, the best thing that you can do is just to be upfront about that and say there's some uncertainty about our results. And this is totally fine. We see researchers doing this all the time. So for example, say that you gather data on levels of stress in college students and you only gather data from one university. This is something that's very, very common in psychological research. It could be the case that the levels of stress in one given university are not generalizable to other students at other universities. And that's okay. You just have to make sure to note that in your results, that your results might not be generalizable because they were not randomly sampled. So that's important to note. If there is little uncertainty, you can reach a conclusion about a population even if you have small risk of being wrong. So if you are more sure, you can kind of state that and be like, hey, you know, we gathered a random sample from our population, so our results are pretty generalizable to that population. However, we can never prove or be 100% certain because we're not using that population data. Because we're using a sample or a subset of our population, we can never be 100% certain, so we can never use the word prove in research when we're using samples. So that's something that's very important to note. We never use prove, we never use 100% certain because we're using sample data. So in order to obtain a random sample, so this is getting at what we need to do in order to get a random sample. And like I was saying earlier, it's very difficult to do this in the real world, and you'll see why here. So the first thing that we need to do is define the population. So how many people are in the population? Who do we need to gather data from? So we need to define that population. Next, we need to identify every single member in that population. So say your population is US voters. That's a lot of people that you've got to define and count every member. Next, you're going to select numbers in a way where every sample has an equal probability of being selected. So this is that randomization piece, which is also very difficult to do in real world situations. So you need to have all these criteria in order for it to be considered a random sample. And this is very difficult to do in the real world, so we usually do bias samples, which we'll talk about in a minute. Oh, here we go, bias sample. So a bias sample is a sample selected in such a way that not all samples from a population have an equal chance of being chosen. So we can try to get pretty close to being a random sample, but because it's so difficult to do it, we mostly use bias samples. So we can do this in a systematic way, or over or under selecting of groups. So say that we are interested in a certain ethnic group for our study. So say that we are interested in Latino Americans, and there's a small proportion of people who identify that way in our university. So we might oversample those people because of that, because we're interested in that subset of the population. So we might systematically oversample in that instance. With a bias sample, every sample of a given size does not have an equal opportunity of being selected. So again, we don't meet that rigid criteria of a random sample. So this is what distinguishes it. We want to try to avoid bias samples and go with our random sampling. However, it's very difficult to do this in real life. So it's often done. We often use bias samples. What else? Researchers want to generalize to the population at large. So we can use techniques besides random sampling which produce similar results. So the goal is always to generalize our results from our study to the population at large. So it's important to use those random samples so that we can be more certain about our generalization. So one goal is to generalize our research, and another goal, which we'll really talk about in chapter 9 and 10, is to determine whether 2 or more treatments produce different results. So do we have significant differences between 2 different groups? So hold on to this piece, the second bullet point, until about chapter 10. We'll talk more about this then. But right now, this is really more important to us. We want to generalize our results to the population at large. Okay, so here we're getting into some of the vocabulary that's used in sampling distributions. So we have our own kind of vocab here. The mean for a sampling distribution is called expected value, and it's denoted like this, E x bar. The standard deviation of a sampling distribution is called standard error, and it's denoted like this. And this is the formula to find it. So here's the symbol for standard error. It's our lowercase sigma with a subscript of x bar. So you can also write it like this. Where's my marker? So that is our standard error term. And we find that by finding the square root of our n in our sample and putting that over our population standard deviation. So this is expected value, the mean of our sampling distribution. Standard error is the standard deviation of our sampling distribution. So here are some characteristics of our sampling distribution. Every sample size is random, drawn from a specified population. Every sample size is the same. The number of samples is large, and the reason that it's large is because when we have larger numbers, we can better generalize to the population. The mean is calculated from every sample, and then the sample means are arranged in a frequency distribution. So here are some different characteristics of sampling distributions. It's not super important for you all to know this for the test or anything. This is just kind of for your reference. This, however, is pretty important. So the central limit theorem is a really interesting phenomenon that happens in statistics. Okay, so like I was saying, the central limit theorem is a really important and interesting phenomenon. Let me go ahead and share my screen again. Here we go, okay. So the central limit theorem states that the sampling distribution of the mean approaches a normal curve as n becomes larger. So basically what that's saying is, as our sample becomes bigger, our distribution becomes more normal. And this is regardless of the distribution's original form. So we see that as n increases, our distribution becomes more like a normal bell curve. So this is a really interesting phenomenon. So like I was saying earlier, the central limit theorem works regardless of the original form of the distribution. So if our form of the distribution was originally skewed, the more numbers that we get, the more n that we have, the higher n that we have, the more normal it becomes. So this is basically the central limit theorem in the gist. And the reason that this happens is as our n increases, our standard error, this thing, our standard deviation of our sampling distribution, decreases. So as n increases, standard error decreases. And because of that, our distribution becomes more normal. So how big do we need our n to be before our distribution becomes normal? Well, originally, or traditionally, the magic number was 30. However, as we have become more savvy in statistics, we see that there are some caveats to that. However, this is kind of the rule of thumb. If the population itself is symmetrical, you may need less. However, if it's severely skewed, you may need more than 30. So it really just depends on the case, what the original distribution looks like. But yeah, that's the central limit theorem. So the central limit theorem does not apply to all sample statistics. So this is a good point that I wasn't mentioning earlier. The central limit theorem only applies to sampling distributions of the mean. So only referring to means of different samples in a population. It doesn't apply to median, standard deviation, variance, correlation, coefficient. So it doesn't apply to that. It only applies to the mean of sampling distributions. So we get more statistical power when we increase our n. So that's another thing that we get. So as our n increases, oh, that's kind of hard to see. Let me just type it out. So as our n increases, our standard error decreases, and our statistical power, which we'll talk more about in Chapter 9, increases. So a lot of things are dependent on our n, our size of our n. So that's important to keep in mind. The effect of sample size on standard error, so that's basically what I was saying earlier. As n gets larger, standard error of the mean gets smaller. So I was basically saying this earlier. As n increases, standard error decreases. So this is probably the last important point of the chapter. So we can also find, this is how we find our z-scores when we're using sampling distributions. So it's very similar to the z formula that we were using earlier. However, at the bottom, instead of using standard deviation, we're now using standard error. And the reason that we're using standard error is because we are now using sampling distributions. So the original z formula that we were working with looked like this. Z equals x minus u. So that was our original z formula. We had our raw score, our population standard deviation, and our population mean, and our population standard deviation. So that's when we're working with raw scores. However, when we're working with sampling distributions, we've got a sample mean, we have a population mean, and we have a standard error. So those are the pieces of the z formula when we are working with sampling distributions. And we can find out the probabilities of certain events happening because we have our theoretical and empirical distributions overlapping one another. And that is that. So those are the slides for Chapter 8. Now we can go ahead and jump into some practice problems. Okay. So here's a good example of how to work with sampling distributions. So the prompt says, a population has a mean of 50 and a standard deviation of 12. For a sample of 4, what is the expected value and what is the standard error? So if you remember back from the lecture a minute ago, I said that the expected value here is just the mean of a sampling distribution. So this one's super easy. It's just 50. Because that was our mean. So the answer here is 50. The next thing that it asks for is standard error. And remember that standard error is the standard deviation of a sampling distribution, and we find it by using this formula here. So we use our population standard deviation and put it over the square root of our n. So in this case, our population standard deviation is 12. Our n is 4, 12, and 4. So we just put 12 over the square root of 4. So we get that our standard error is 6. So pretty simple stuff there. Now, what if I wanted to do the same thing but gather a bigger sample? So what if I wanted to change this n to 36? Say I increased my sample because I realized that that gives me more statistical power. So I go out and I get 36 people instead of 4. How does that change this? Well, our expected value is still going to be the same because our sample mean is the same. Or I'm sorry, our population mean is still the same. Our population standard deviation is also the same. We just have a bigger sample this time around. So our expected value is going to be the same. However, this stuff down here for standard error is going to change. All we've got to do is change the denominator because our population standard deviation is the same. So here, we just do square root of 36. 12 over 6 gives us 2. So we see that our standard error decreased when we increased our sample size. So this is basically what I was saying earlier. When we increase our sample sizes, n goes up, our standard error goes down. So this is a good way to illustrate that, a good example of that. Okay, this is a different kind of example. This is basically what we call the z-test. So this is an example of a z-test problem. So the prompt says, a researcher is interested in the effects of a herbal supplement on memory. So our herbal supplement is the independent variable, memory is the dependent variable. Population memory scores have a mean of 80 and a standard deviation of 18. So that's our population data. A sample of 36 people were given that supplement, and their memory score had a mean of 84. So the question asked, is the sample significantly different from the population? So that's basically our goal here, is to see if our sample is different from our population. And we do that by running a z-test. So here, we're going to use our z formula that we talked about earlier, where we have our sample mean, our population mean, and our standard error. And our standard error formula is down here, where we find our population standard deviation and put it over the square root of n. So we have all of our pieces to find this out. All we have to do now is put them all together in the formula. So we have z. Actually, the first thing that we need to do is find our standard error, because that goes into our z formula, so we'll need to find that first. So standard error. In this case, the first thing that we need to do is find our population standard deviation first, which was given to us in the problem. That is 18. 18. We put that over the square root of n. And our n is 36. So square root of 36. 18 over 6 gives us 3 for our standard error. Next, we're going to put that into the z formula. And again, we have all these pieces already. We have our sample mean, that's 84. We have our population mean, that is 80. And we have our standard error, which we found in the previous step, was 3. 4 over 3 gives us a z-score of 1.33. So that's how you find your z there. Now this is getting a little bit ahead of ourselves, but if you're interested in how to find whether or not our sample is different from the population, this is how you would do it. You're not going to have to do this for your test this time around, but it's something that we will do in Chapter 9. So if you're interested to figure out how our sample is significantly different from our population, you would do it this way. So here's our z-score. This is really the only, this is the last step for the test that I'll have you do, is basically just finding the z. You're not going to have to interpret whether that z is significantly different or not. If it's a significant result, you'll just have to find that z. But if you're curious, this is how you would do it. So if you remember from our Chapter 7 lecture, I talked about the point at which our results become statistically significant. And if you remember, there was a z-score associated with what point denotes when our data becomes statistically significant. And if you remember, that z-score is 1.96 on each side of the distribution. 1.96 positive, 1.96 negative. In order to determine whether or not our answer is significant, we've got to see if it falls in the shaded region. So does 1.33 fall past 1.96 is the question here. And the answer is no, it doesn't. 1.33. It doesn't fall in the shaded region. And because it doesn't fall in the shaded region, our sample is not significantly different than our population. So that's how you would do a problem like that. Like I said before, you'll only have to get to this step for the test. That's all I'm going to ask you to do this time around. However, later on, we'll have to start making these determinations about whether there's a significant difference. So that's how you would do something like that. All right, here's another type of problem. So this is a common one that you might see on your quiz. So it says that a sample of 3 was taken from a population that has a mean of 5 and a standard deviation of 2. The raw scores for that sample were 2, 4, and 6. So these are the scores from this sample up here. And then the question asks, what is the probability of obtaining this sample, of this sample mean, or one that's less than that? So we've got a lot of stuff happening here. So the first thing that we need to do, we need to write out our formulas because that's going to be helpful. So again, we've got our z, our sample mean minus population mean over standard error, where our standard error equals population standard deviation over square root of n. So the first thing that we're going to do is find our sample mean because it's asking what is the probability of obtaining this sample mean. So we've got to find that sample mean first. And if you remember, to find sample mean, all we have to do is add up our scores and divide by n. So we're going to go 2 plus 4 plus 6 over 3 gives us 10, 12, or 3 is 4. 4 plus 2, yeah, 6 plus 4 plus 2, 12, 11, 3 gives us 4. So that's our sample mean, 4. Now, we have all the pieces we need to go to our z formula that I have over here. So before we move to z, we've got to go and do our standard error first because we've got to find standard error in order to find z. So standard error comes next. So our population standard deviation was given to us, that's 2. That's 2 here. 2 over the square root of n, which was 3. Square root of 3 is 1.73. So 2 over 1.73 gives us 1.16. So that's our standard error. Next, we've got to find our z-score. We have our sample mean here, so that's what comes first. 4 minus our population mean, which is given to us 5, over our standard error, which we found in our previous step was 1.16. We have negative 1 over 1.16. 1 divided by 1.16 gives us a z-score of negative 0.86. So that's your z-score. So this is the z-score that we came up with. So the problem asks us, what is the probability of obtaining this sample mean or one less? So like I was saying with the previous chapter, it's really important to draw out what it's asking. So I'm going to erase our formula so that we've got a little bit of room here, so that you can see what I'm talking about. So the question asks for what is the probability of obtaining this sample mean or one less. So let's go ahead and draw our lovely bell curve. Remember that 0 goes in the middle. That's always the mean. Our z-score is negative 0.86. So that's our z-score. The question is asking, what is the probability of obtaining this z-score or one less? So it's asking for everything to the left of the distribution here. And if you remember from our previous lecture, when it's asking for the ends of the distributions, the extreme, the appropriate column that we want from our z table is our z to infinity column. So z to infinity. So let's go ahead and jump to that table. Okay, so here's our z table. So the z-score that we are working with is negative 0.86, but if you remember from our previous lecture, all of our z values are absolute values in the table. So we just look for 0.86 in our column A. So here we're looking for 0.86 in our column A. And we see that it's right here, 0.86. Like I said earlier, we're going to be using our z to infinity column because that's what's dealing with the outskirts of the normal curve, the extremes. So here we are looking for column C because that is our z to infinity column. So 0.86 z to infinity, we see that our probability associated with that is 0.1949. Or 19.49%. So the answer to this problem is 19.49% of the distribution is associated with a z-score of negative 0.86 or less. So that's how you would do a problem like that. It's similar to one that you will be doing for a quiz. All right, so here's another type of problem that might be on your quiz and or test. Let me even this out there. There we go. Okay. So what is the standard error for the following sample? And we've got some summary data here. We're told that the sum of our x squareds is 50, sum of our x is 15, and we have a sample of 6. So here are the relevant formulas that we're going to be using for this problem here. We're going to need, of course, our mean formula. We're going to need our standard deviation formula. So these are all on your formula sheet on Moodle. And so the standard error when we're just working with samples is the exact same formula that as the population, except instead of population standard deviation, we have sample standard deviation on the top. We still have square root of n. So these are your relevant formulas. You've got your mean, standard deviation, and standard error. So what do we do first? Well, we can find our mean first. We do that by finding the sum of our x over n, and we're told that the sum of our x is 15. Our n is 6. When we do that division, we get 15 divided by 6 is 2.5. So that's our sample mean. Next, we find our sample standard deviation. We're told the sum of our x squareds, which comes first in that formula, is 50. Next, we've got to do a little deducing here in order to get the sum of our x's then squared. We have the sum of our x's, so now all we've got to do is just square that number. So 15 squared is 225 over n, which we're told is 6, over 6 minus 1. So 50 minus 225 divided by 6 gives us 37.5 over 5. When we do all that math, we get 50, 50, 2.5, we do the square root. So our standard deviation that we should get is 1.58. So that is our sample standard deviation. And then lastly, we're going to put that into our standard error formula because that's what the problem is asking for, standard error. So first thing we do, sample standard deviation, 1.58, which we found in the previous step. And then we put that over our square root of n is 6 in this case. 1.58 over the square root of 6. 2.44 is the square root of 6, or 2.45, I guess. You do that division, 1.58 divided by 2.45, we get 0.645. So this will be your final answer when asked for the standard error for the following sample. So 0.645 is your standard error for this one. All right, so here's the last kind that we're going to do. So the problem says when you have a population mean of 5, population standard deviation of 2, and an n of 3 for a sample, what proportion of the means for sample means are 4 or less? So what proportion of our sample means when we have a sample standard deviation, or a sample sampling distribution rather, are 4 or less? So of the possible samples that we have in a sampling distribution, how many of them are 4 or less? So again, we're going to be using that Z formula that we talked about during this lecture. So that's this one here. Z equals sample mean minus population mean over standard error, where our standard error is population standard deviation over the square root of n. So the first thing we're going to do is we are going to find the z-score that is associated with a sample mean of 4. And we have all the information to do that. Z equals 4 because that's my sample mean, minus 5 because that's my population mean, over standard error, which we can just go ahead and put into one formula to make this a little more simple. So that's population standard deviation 2 over the square root of 3. So this is another way that you can kind of write this Z formula. You can put it all into one instead of breaking them up into 2. So here is your standard error formula. I've just put it here. I've made it one big equation instead of 2 separate ones. So you can also write it this way as well. This is usually how I do it because it's a little faster. So in the numerator here, we've got -1 over 2 square root of 3, 1.73. One over 2 divided by 1.73 gives us 1.16. 0.86. I'm sorry, negative 0.86. So that's your z-score that we found, negative 0.86. So the problem asks, what proportion of means have a sample mean of 4 or less? So we converted that sample mean raw data into a z-score. Now we're going to find out what proportion of the distribution is associated with that z-score, or 1 less. So again, we're going to draw it out. There's our bell curve. 0, of course, always in the middle. 0.86 falls on the left. It's pretty close to the mean because it's a decimal point. So this problem is asking for 4 or less, so that means we are looking for the left side of the distribution. So if you remember, the column on the z table that we're going to be looking for is z to infinity, because we are working with the outskirts of the z distribution. We're working with the tails of the distribution. So we want z to infinity, or column C, as it's called on that table. So let's look up z to infinity for 0.86. So here's our z table. Column A, we find our z-score, 0.86. Column C, z to infinity is what we want. 0.86, we scroll over here. The probability that's associated with that is 0.1949. So 19.49% of the distribution is associated with a sample mean of 4 or less. That is how you would interpret that. So let me say that again. 19.49% of the distribution is associated with a sample mean of 4 or less for these numbers here, for this population. So that's how you would do that kind. So those are all the practice problems that I have for now. If you have any questions, again, feel free to email me with those.